Today, we will graph quadratic equations in vertex form. Y equals a times the quantity x plus h squared plus k. Let's revisit how we graph lines. We have three formulas when graphing lines: slope-intercept form, point-slope form, and standard form. The form that we use the most when graphing is slope-intercept, though the other two are used. Standard form is we usually use it if we're looking for intercepts and graphing intercepts. Point-slope form is the one that we tend to not use, but we actually are using it every single time we use slope-intercept form, because slope-intercept form is a special type of point-slope form when that point is on the y-axis. So when graphing y equals 3x plus 2, we begin at 2, which is actually the point 0, 2 on the y-axis, and then we move accordingly. We use our rise over run. In this case, our slope is 3, so we write it as 3 over 1. We go up 3, right 1, point, up 3, right 1, point, and connect the dots. Point slope form, which is y minus y sub 1 is equal to m times x minus x sub 1. We have our slope, and then we have our point. Notice that we have y minus and x minus, and we're just pulling out the point. So you can consider these being the opposite of what's inside this parentheses and what's on this side with the y. If our slope is 3 and the point it passes through is 1, 2, okay, so the 3 will go there, the 1 will go there. So when we look at this, what point were we using? We were using point 1, 2. So when we write this, if I say, hey, what point is this passing by? Name a point that this line passes through. You would simply say the opposite of this. The opposite of, you see this minus 1, so it's simply just 1. And the opposite of this, you see a minus 2, you'll simply say 2. So when we're graphing, we begin at 2, 1. We can say we begin at 2, 1 and move accordingly. Up 3, right 1, up 3, right 1. So we really don't have to start at the y-intercept. If we wanted to start at the y-intercept and graph this, we would see that our y-intercept is actually -5. If we wrote this equation in slope-intercept form, this is where we'll start, and you can see that graph will actually go through that point, 0, -5. So again, when we write this in point-slope form, the point that we're actually passing through is not -4, -9, it's actually 4, 9. And when we have a negative, minus a negative is actually just +1. Therefore, the point that we're passing by, it wouldn't be 1, it would be the opposite of this, which would be -1. And the opposite of a -8, which would be 8. The three forms that we write linear equations are point-slope form, slope-intercept form, and standard form. When we see this particular equation, this is as if it's telling us to start at the point 0, 1, just like this equation says to start at 0, 1. That's our y-intercept. 0.01, and then we just move accordingly. Up 3, right 1, up 3, right 1, connect. This is going to be very similar to what we will do today when graphing quadratic equations. The vertex form of a quadratic function is f of x is equal to a times the quantity x minus h squared plus k, where a does not equal 0, and h, k is the vertex. The moment I look at this, you can see how this has a minus sign. So whatever's inside this parentheses, it will be the opposite. And k has a positive side, so it will be the same number. So we change the sign and we leave the sign. So when looking at the first case, we can see our vertex would be the opposite of a +2 and the same as 7. So we write our vertex as -2, 7. The next one, the opposite of a -5 and the same as +2. So in this case, this would be 5, 2. In this particular case, we can see that we do not have a h. Therefore, If there's not an h, the h must be 0. And we have our k, 0, 9. In this particular case, our k is 0. And remember, we're writing the opposite of our h. So -1, 0. Use the given vertex to write a quadratic function. When we write this one out, remember f of x is equal to a times x minus h squared plus k. So h, when we write down h, we're going to say minus 3 and plus 2. On the next case, since there's already a minus a negative is a plus 4, and then plus 0, which we don't have to do. So it would look something like this. Minus a negative is a plus 4, and when we add 0 to anything, it's the identity property. We just get itself. And on this particular case, it's x minus 0, so it'd just be x squared minus 5. So again, if you're looking at it, it's minus 0, and again, 0 is the identity property, so we're going to be left with just x. And that looks like so. When graphing using vertex form, if you want to go back to how we graphed it before, you could, but I wouldn't see why, especially when it's already in vertex form. We can multiply this out. And on our do now, we went over how to square a binomial. We can just add our like terms. For minus 7 is a minus 3. When you see this, there's no need to calculate the axis symmetry. The axis symmetry is already given. -2, -7. Then we could just use our step pattern. 1, add 3, add 5, add 7, and you're done graphing. Now, you could, if you wanted to, multiply that out. Then you have to find the axis symmetry, plug it in to find the vertex. Then, but we already have this. Why do this work? And that's why we like it, because we already have the vertex. That's the point where we want to start. Just like the point we like to start at is the y-intercept when we're graphing lines, the point we want to start at when we're graphing quadratics is the vertex. When it's in vertex form, we have it. Just like when it's in slope-intercept form, we have that y-intercept. When graphing, if you have the vertex, you could just use the step pattern. We start here, right 1, up 1, right 1, up 3, right 1, up 5, right 1, up 7. And then you just match the left side and then connect. Now you could always use, if you have the table, plot the points, but it's a lot quicker just to go count, right 1. And then it's great to check to make sure 2 9s here and 2 9s there, and then you're good to go. So in this particular case, we should know that our vertex is 2, -8. I'm going to go by increments of 1. My A term is 1, so my step pattern will simply just be 1, 3, 5, 7, 9. So we add 1, add 3, add 5, add 7. I usually like to check the last one just in case. A lot of times I'm working quickly and I forget that it's not a 1 and my step pattern will change, or maybe it's a negative, or maybe I just added wrong. So it's great to check that last one. So when I check it, I'm going to plug it in, simplify, and I get y equals 8. So my point should be 6, 8. Graphing, again, start here, right 1, up 1, right 1, up 3, right 1, up 5, right 1, up 7, and then match the left-hand side. And connect. And you can see, hey, we have 6, 8, and 6, 8. On this one, we should see that our vertex is -1, 5. So therefore, our step pattern changes. It's not plus 1, it's going to be minus 1, then minus 3, then minus 5, then minus 7. So subtract 1, subtract 3, subtract 5, subtract 7. And again, great to check that last one just to make sure. And plug in 3, we get 4, 4 squared, negative 16 plus 5, it's negative 11. And then it works out. And again, when graphing, I love the step pattern. Now it's going to be write 1 down 1, write 1 down 3, write 1 down 5, write 1 down 7. And then match the other side. Again, you do not have to use a step pattern. You could use your table to graph, but it's just a lot faster when you use a step pattern. And let's take a look at this one. The vertex is 3, negative 6. My step pattern changes because my A term is a 2. So instead of being 1, 3, 5, 7, 9, it's 2, 6, 10, 14, 18. So add 2, add 6, add 10, add 14. Always try to check that last point to check your work. And when we substitute 7, you get 4. 4 squared is 16. 2 times 16 is 32. 32 minus 6 is 26. So that's 7, 26. So when graphing, it's going to be plot the vertex, and then write 1 up 2, write 1 up 6, write 1 up 10. And then match the left hand side and connect. And again, if you wanted to use a table, you may do so. All right, let's solve this equation. There's several ways that you can solve it, but the method that we're going to factor, and then we're going to take the square roots. So let's take a look at this. So again, the first thing is it looks like it's a perfect square trinomial, but let's do a quick check. We're going to take that middle term and divide it by 2. And then we're going to take the square root of the leading coefficient. The square root of 1 is 1, times that by the square root of the constant. The square root of 25 is 5, and we're just taking the principal square root. And notice that 10 divided by 2 is equal to 1 times 5. And this is what we're doing in our heads. So therefore, I know I can factor this out to x plus 5 squared. We can solve this by taking the square root of both sides. That leaves us with the absolute value of x plus 5 is equal to 0. Then x plus 5 equals plus or minus 0. Subtract 5 from both sides, and we are left with x equals negative 5. Most teachers will skip that step, so I'm just showing it to you because sometimes you actually need the absolute value, especially when you get to algebra 2. So let's take a look at this one again. Remember, the leading coefficient here is a 1, and we're going to take half of the middle term, and then we're going to take the square root of 1, which is 1, and multiply by the square root of 49, which is 7. Notice that 14 divided by 2 is 7, and 1 times 7 is 7. Therefore, I know it's a perfect square trinomial. So therefore, I can factor it out to x minus 7 squared is equal to 0. Now we're just going to take the square root of both sides. That leaves us with the absolute value of x minus 7 equals 0. X minus 7 equals plus or minus 0. Add 7. X equals 7. In this particular case, we have a leading coefficient of 4. So we'll take half of the middle term, 36 divided by 2. The square root of 4 is 2 times the square root of 81, which is 9. And we can see that 36 divided by 2 is 18, and 2 times 9 is 18. Therefore, this is a perfect square trinomial. So we have 2x plus 9 squared is equal to 0. Take the square root of both sides. We are left with the absolute value of 2x plus 9 equals 0. So then 2x plus 9 equals plus or minus 0. Subtract 9 from both sides. We are left with 2x equals negative 9. Divide both sides by 2. X is equal to negative 9 over 2. Let's check to see if this is a perfect square trinomial. We'll take half of 42, which is 21, and the square root of 9 times the square root of 49. So that's 3 times 7, and that is also 21. Therefore, I know this is a perfect square trinomial. And remember, this has to be a positive. If this is not a positive, I already know it's not a perfect square trinomial. The constant has to be positive. Take the square root of both sides, add 7 to both sides, divide by 3. So x equals 7/3. So what constant will make the binomial perfect square? What would I have to add to this? So similar to what we did, we're taking half of this number, which is 7, and squaring it. And now we have a perfect square trinomial, because we know that 14 divided by 2 is equal to, remember there's an understood 1 here, 1, the square root of 1 is 1, times the square root of 49, which is 7. So it's equivalent to that. So the number that we're adding is 49, that's our answer. So again, on this particular case, what are we adding? What's half of 30? 15, and 15 squared is 225. And we can just check it. This case, what's half of 9? 9 over 2. We're going to use fractions. If you have a calculator, yes, but you want to really use fractions. 9 over 2. And 9 over 2 squared is 81 over 4. And we can check it by taking half of the middle term, 9 over 2, which is the same as the square root of the leading coefficient, which is 1, and the square root of 81 is 9, the square root of 4 is 2. 1 times 9 over 2 is 9 over 2. So our answer is 81 over 4. Similar situation, we divide 3 by 2 and square it. That will give us 9/4. And we can check our answer by taking half of the middle term and taking the square root of the leading coefficient times the square root of the constant. And we can see that we get 3 over 2. All right. This is going to help us when we have to solve by completing the square. When we say completing the square, we actually want to have a perfect square trinomial. When we do this, what would I have to add to make this a perfect square trinomial? Well, half of 10 is 5. 5 squared is 25, so we'll add 25. This will leave me with x squared plus 10x plus 25 is equal to 25. The left-hand side is a perfect square, so therefore we could factor that out to x plus 5 squared is equal to 25. Now take the square root of both sides. The absolute value of x plus 5 is equal to 5. Therefore, x plus 5 is equal to plus or minus 5. We can subtract 5 from both sides, and we'll be left with x equals -5 plus or minus 5. So we have two answers, x equals -5 plus 5, or x equals -5 minus 5. This will leave me at 0 or -10. You might be looking at this question and said, we solved this question already using a different method, and it didn't involve all this work. And that's when we solved it by factoring, GCF factoring. We factor out the x, so we have x times x plus 10 equals 0. Then we use a zero product property, seeing that x equals 0 or x plus 10 equals 0, and solve. Unfortunately, when we have a constant factor, we can't solve in this manner. We will need to solve by completing the square. So again, we'll eliminate the constant from the left-hand side by adding a. In this particular case, when we have a constant, we won't be able to solve it using the zero product property in that manner. We will have to solve it by completing the square. We'll add 8 to both sides. That leaves me with x squared plus 10x is equal to 8. Then we'll take half of 10, which is 5, and square it, which is 25. So we'll add 25 to both sides. That will leave me with x squared plus 10x plus 25 is equal to 33. On the left-hand side, it's a perfect square, so we can factor that out. Write it as x plus 5 squared is equal to 33. Take the square root of both sides. That leaves me with the absolute value of x plus 5 is equal to the square root of 33. Therefore, x plus 5 equals plus or minus the square root of 33. Subtract 5 from both sides. We're left with x is equal to -5 plus the square root of 33. That means we have two answers, x equals negative 5 plus the square root of 33, or x equals negative 5 minus the square root of 33. They're not like terms, so this is your final answer. X equals negative 5 plus the square root of 33, or x equals negative 5 minus the square root of 33. Let's take a look at another example. We will need to solve by completing the square. So we'll add 9 to both sides. First, to complete the square on the left-hand side, we'll have to take half of 4, which is 2, and 2 squared is 4, so we'll add 4 to both sides. Since the left-hand side is a perfect square now, we can factor it to x plus 2 squared. Take the square root of both sides. So we're left with the absolute value of x plus 2 is equal to the square root of 13. That means that x plus 2 equals plus or minus the square root of 13. Subtract 2 from both sides, and we're left with x equals negative 2 plus or minus the square root of 13. Therefore, x is equal to negative 2 plus the square root of 13, or x is equal to negative 2 minus the square root of 13. And let's solve this one by completing the square. So the first thing we're going to do is eliminate the constant from the left-hand side. So we'll add 11 to both sides. Now we can complete the square by taking half of 2, which is 1, and 1 squared is 1. So we'll add 1 to both sides. On the left-hand side is now a perfect square, so I can factor it. Now take the square root of both sides. This radical can be simplified to the square root of 4 times the square root of 3. Remember, 4 times 3 is 12. Now we know what the square root of 4 is, it's 2. That's why I factored out the perfect square. So you always want to try to factor out your largest perfect square when you're solving this. So that means that x plus 1 equals plus or minus 2 times radical 3. We could subtract 1, so x equals negative 1 plus or minus 2 radical 3. So x equals negative 1 plus 2 radical 3, or x equals negative 1 minus 2 radical 3.